A function y equals f of x has both a maximum and minimum value. These values are termed maxima and minima. The maximum of a function is the highest value that it reaches over a closed interval, whereas the minimum of a function is the lowest value. Locating the maxima and minima is not only a concept applied in mathematics, but can also be useful in solving real-world problems in fields such as engineering and science. Finding a function's maxima and minima can be separated into two parts. Firstly, finding the stationary points of the given function, and secondly, determining the nature of these points, that is, whether they are a maximum, minimum, or a point of inflection. Function y equals f of x has a local maximum at a point when the y value is greater than at any other point in the immediate neighbourhood. This means that on either side of the local maximum, the function moves in the same direction, that is, downwards. On the other hand, a local minimum is a point where the y value is less than any other point in the immediate neighbourhood. That is, the function to the left and right of the point extends upwards.
The derivative is the function that displays the slope of the curve. The points of a function where the slope is equal to 0 are known as stationary points, and in order to locate these points, the derivative must be equal to 0. Once these points are found, you will need to determine what type of stationary point they are. There are three types of stationary points. The two most common are local maxima and local minima. Where the derivative is 0 but neither a local maxima nor a local minima, it is called a stationary point of inflection. There are two methods that can be used when determining whether stationary points are a maximum, minimum, or point of inflection. The first method is the second derivative test. I'm going to use an example to demonstrate this concept to make things a little simpler. Let's say the example is to find where the local extrema occurs for the function x to the power of 3 minus 3x. Now the solution, step by step, is firstly to find the derivative of the function. So the first derivative of the function is 3x squared minus 3. We then place a 0 and solve. The common factor here is 3, so 3 bracket x squared minus 1 equals 0. We then divide both sides by 3, so x squared minus 1 equals 0. And then we figure out the critical points. Now if we factor this out, we get x minus 1 and x plus 1. So our x values are x equals 1 and x equals negative 1. We then continue on to find the second derivative. So the second derivative equals 6x. If we substitute the value x equals 1, we get 6, because 6 times 1 equals 6. And if we substitute the value x equals negative 1, we get negative 6, because 6 times negative 1 equals negative 6. So we note that the second derivative exists if the outcomes or solution is a real number. So when we substitute in x equals 1, we get 6, which is greater than 0. Therefore, the function has a local minimum at the point x equals 1, because it is positive and the slope is increasing. When we substitute the value x equals negative 1, it is less than 0, because it is negative 6, and therefore the function has a local maximum at the point x equals negative 1, because it is negative and the slope is decreasing. And those are the x values to locate where the local maximum and local minimum are in the function x to the power of 3 minus 3x. Now I'm going to show you a summary of the outcome of the second derivative test and how we are able to determine the nature of the stationary points. So if the function is less than 0, this means negative, or the derivative is decreasing and so the slope is decreasing. Therefore, we have a local maxima. If the function is greater than 0, this means positive, or the derivative is increasing, and so the slope is increasing. Therefore, we have a local minima. If the function equals 0, the test fails and tells you nothing, and you must use another method to determine the nature of the stationary point. If we think about it, an easy way to remember is if it is a negative sign, it is a sad face shape or an upside down smile. Therefore, it is a local maximum. Whereas when the outcome is positive, it is a smiley face shape, and therefore a local minimum.
Using the first derivative test, we can determine the nature of the stationary points by examining the sign of the first derivative immediately to the left and right of the point. If the derivative is negative for the x value less than a, and positive for x greater than a, then the graph is decreasing to the left of the stationary point and increasing to the right. This is a local minimum. If the derivative is positive for x less than a and negative for x greater than a, then you have the opposite, a local maximum. However, if the derivative is negative for both x less than a and greater than a, then you have a point of inflection. This stationary point also occurs when the derivative is positive for both x less than a and greater than a. As an example, we will find the nature of the stationary points of the function y equals 3 times x to the power of 3 minus 9 times x plus 6 using the first derivative test. The first step is to find the derivative by differentiating the given function once. This gives us three factors: 9, which will always be a positive, x minus 1, and x plus 1. Now to find the stationary points, solve for x minus 1 equals 0, and x plus 1 equals 0. The two stationary points should occur when x equals 1 and minus 1. The second step is to find the nature of the stationary points at x equals 1 and x equals minus 1. For the first derivative test, we refer to the points immediately to the left of x equals a and immediately to the right of x equals a. In other words, we substitute x equals a minus a little bit and x equals a plus a little bit into each factor in order to determine whether the stationary point is a maximum, minimum, or point of inflection. For the first stationary point, when x equals 1 minus a little bit, the first factor of the derivative, which is 9, is a positive. The second, x minus 1, is a negative, and the third, x plus 1, is a positive. This means the derivative is the product of a positive number, a negative number, and a positive number, therefore will equal a negative number. When x equals 1 plus a little bit, again the first factor and x plus 1 are positives. However, this time x minus 1 is also a positive, thus the derivative is a product of three positive numbers, resulting in a positive number overall. This information can then be sketched. For negative numbers, the graph decreases, and for positive numbers, the graph increases, displaying a local minimum at x equals 1. This step is then repeated for each stationary point, in this case x equals minus 1, where it can be concluded that there is a local minimum.
Our global maximum and global minimum are our highest and lowest points out of all of the peaks. It can only ever be a stationary point or an endpoint. The steps to locate the global maximum and global minimum are to find the endpoints, find the stationary points, calculate the functions and create a list of candidates, and to select the smallest and largest points out of these values. So now we'll work through an example to fully grasp the concept. We are going to find the global extrema, or absolute minimum and maximum, of the function 1 plus 2x to the power of 3 minus x to the power of 4, with endpoints -1 and 2. So first step is to locate the endpoints. Well, they've already been given in the question, so the endpoints are x equals -1 and x equals 2. We then find the stationary points, so we find the derivative. We get 6x squared minus 4x to the power of 3 equals 0. Continuing to solve it, we get 2x squared bracket 3 minus 2x equals 0. Calculating the outside against the 0 and the inside of the brackets against the 0, our solution becomes x equals 0 and x equals 3 over 2. We then calculate the functions with the values of x and create a list of candidates. So when we substitute -1, we get -2. When we substitute 2, we get 1. Substituting 0, we get 1. And substituting 3 over 2, we get 2.688 to 3 decimal places. Now we've provided a list of candidates, we move on to step 4, which is selecting the smallest and largest of the values. With this, we come to the conclusion that at the point x equals -1 is our global minimum, as it is the smallest value at -2. And at the point x equals 3 over 2, our global maximum, as it is the largest value at 2.688. We hope you have been able to grasp the concept and understand the applications of maxima and minima, and good luck with calculus.